Hi. Here.
There's someone like at work, so I'm covering their shift last minute, so like, it starts at 5, but like,
Right.
I have hours of leave, we were just in the class, and so I
Yeah.
just don't want you to think like. how my-
That's all right. Yeah, that's good. Well, why don't I can just get started, I think, because probably everyone's here that's gonna come, but anyway, so Tuesday, we have the P&G person coming, right? So anyway, and it'll be, yeah, it's gonna be, well, it's gonna break up, so it's more than this class to finish the bioplastics, so it's gonna be 3 speakers in a row. 28th is Thanksgiving. Actually, we're like at the end, right? And the third, I have this that person. So we have the 5th. So actually, I might not finish bioplastics. Like the slides will be there, but basically the 5th, I might just go through overview or something like that, you know. Oh, and then we have I guess there's a homework, there's like a final homework or something. Is that right? I think that's how I had it. But yeah, there's a final homework that's like individual. And then the grad students have to do their kind of paper. So everyone except one person did the from the grad students. I think there's like 4 or 5 grad students. So everyone did the outline and kind of a summary, except one person's reworking it. Are you guys having any problems with that, or have you started doing anything, or you have? All right, that's good. Yeah, so that hopefully that'll, anyway, if you need help with that or you want to bounce it off me, just send it, you know. Nice, that's good. Yes, it's actually of my lectures is that there's 2 more lectures after this, I guess. No, that's Thanksgiving. There's 1 more lecture. I didn't realize that, but basically, yeah, I'll try to, I mean, we'll just kind of truncate bioplastics. There's a lot to it, you know. I mean, there's a lot, basically the book and then that paper and then kind of whatever else I've dug up from it. So I think it's like 80 slides. Anyway, so yeah, these are the for polyhydroxybutyrate, so polyhydroxybutyrate and PLA are the two main, when people talk about bioplastics, that's what they're talking about. And then there's quite a few companies now that are doing this. So that's a list of the ones that exist, but anyway, it's in commercial production and they're making plastic forks and things with it. You can get plastic, you can get all kinds of plastic sheet, plastic, I haven't seen fibers or textiles from it, so I'm not sure if they've gotten to that point, but basically everything else, like this kind of a list of the companies here. So I don't think there's much, I mean, it's basically like different companies are making this stuff. Anyway, so that's just a list of the companies and without that logos, but and then they keep coming up with new grades for different properties. So this the tuning of PHB has been going on since the 1950s, I think. Like ICI, Imperial Chemical Industries, was a British company in Canada. I think their Canadian division in like after World War II came up with PHB. And then they had the original patent, and then that was transferred company to company. Monsanto had it for a while in the 70s, and then it's been transferred out. And I guess some of the original patents must have expired because it's more than whatever 23 years. Or how long is a patent? 20 years? I think it's 18 maybe. I think it's like 18 years for a patent, and then you get extensions. It ends up like 20 something, but sorry, it's well past that for the original ICI patents on it. So everything else has been like the copolymer patents. P&G had like the valerate, butyrate, and then some of the processing for it are IP too. So still, there must be quite a bit of, so it's saying like new enhanced heat resistance. That's definitely a patent, you know. So anyway, so this patent's still coming out on PHB, even though it's been around since if it was the 50s, it's like 80 years, something like that, right? So it's quite a long time. It almost is longer than some of the commercial plastics that are around. So anyway, so PLA is the other, so PHB is made directly by microorganisms. So you have to separate, you have to do a bio separation at the end. Somehow get the cells out and whatever extra food stock and goo is in it, and then get the plastic from it. But they think that the end of the microbial fermentation is like 80% PHB. So it's a lot higher than what you think. So they drive the bacteria to a point where they're just starving to death or dying. So they eat up themselves. There's nothing left but PHB, and then they stop the reaction. And like it's kind of a nasty thing. I mean, if you think that it's a it's a life form that can feel things, you know. I mean, you're really actually torturing it to make this stuff. But if you don't believe that about microorganisms, I guess you're okay. Anyway, so the Tibetan Buddhists won't want to use this stuff, I think, but it's hard to tell. Anyway, so anyway, the PLA on the other hand, this lactic acid, just like we have it in our body, right? So this is a product of just normal living, and you can get it out from fermentation. If you dehydrate it, it makes a cyclic heteroatom molecule, and that thing pops open. So it's a condensation polymerization, but there's no product. There's nothing condenses because you condensed in the step of making this cyclic monomer. So that's got like ring spring. It just wants to open and polymerize. So it does that. So anyway, that's a kind of a cleaner operation because you can distill a liquid. Like a polymer, you can't distill. So some of the PHB is still going to have some cell things in it, right? But this you can actually distill and dehydrate, and then when you make a pretty clean polymer after that. So this looks like a better, kind of a better option in a sense. They're both polyesters, right? So they both have deesterification, so they both kind of break apart. See, they'll both break apart if the oxygen bond is a weak bond, so it'll break. It can hydrolyze, so. So both of them can be, and that's basically the process of it being biodegradable. So in this case, this is a more stable ester, so that you have to put it under pressure and heat to break that bond. And with a PHB, it just naturally at room temperature can degrade. So PLA's got its own set of like companies that do it, that are involved. So Evonik was a break off from like DSM was a German gigantic or Bayer was a German gigantic chemical, and DSM and Evonik, which was Degussa, are so in Frankfurt. There's a bunch of chemical companies to be all one chemical company. The biggest in the world was Bayer, right before World War II. Then during World War II, some company in New Jersey just took the Bayer name for aspirin. They just stole it, and after the war, the Germans didn't get any IP back, so Bayer aspirin's made in New Jersey, even though Bayer Chemical was once the largest chemical company on earth, right? And they invented a lot of things. Anyway, Degussa was one of the split offs, and it's near Frankfurt. It's like, I think, south of Frankfurt on the Main River is where the plant is that I know of. Basically, they're saying it's in North Rhine-Westphalia. So it's the Main meets the Rhine somewhere there, this Evonik, which was Degussa. Not sure why they changed the name. I mean, maybe Degussa still connects somehow with the Nazis. I think they kind of started losing the names and got some more modern names for some of the companies, you know. But anyway, so they're making PHB too. They make titania, though. That's what I know them for. But anyway, so I'm not sure what this link goes to. It's just something catching. What's it doing? I think it just goes to the Evonik webpage. Oh, it shows some kind of whatever. That's a pretty nice graphic. Anyway, so back. That's there. That's pretty good. No, that's not good. This is what I want. Evonik and this Corbion company, or Total is a French oil company, right? And then I guess Corbion's a branch of that. NatureWorks makes spoons, I know that, but basically the spoons that they make is PHB. So NatureWorks makes a lot of different biodegradable. So I have a link to all these kind of biodegradable. They make PHB and PLA. So anyway, so they're another company. And this is I think this is a Belgian company, this Ferrero, and then Total Corbion. I'm not sure where they are. So the US one, I guess, is NatureWorks. This is German. This is Belgian. These guys are French. It's kind of the European US allegiance, whatever that's called. NATO, I guess. But anyway, so PLA doesn't degrade in a home compost. PHB does. So you need to have an industrial compost, but there isn't any like industrial compost in Cincinnati, as far as I can tell. There's places that claim they are industrial compost, and then what they do is they sell like dirt for $20 a gallon that comes from an industrial compost. Like if you go to their webpage, there's nothing in Cincinnati, even though they say they're in Cincinnati. What they do is they'll go to like farm markets and say like, we're doing industrial composting, and they'll have like a bunch of dirt that you can buy. But they aren't in Cincinnati. And then this Queen City Commons kind of claims to be industrial composting, but if you look like, where can I industrially compost my PLA? It's not in Cincinnati. It's like somewhere else, you know. So anyway, we're in a dead zone of industrial composting. This is a map of all the composting in the United States, I guess. I don't know what year this is, but green is the one you're looking for, and we're here and there's no green. But strangely enough, Dayton has industrial composting, and so does Columbus, and so does Indianapolis. At least they accept fiber compost products only. And then I guess that's whatever Indiana IU, what's that town? What's the name of it? Indiana University. Anyway, there's a town there. It's a pretty nice place to visit. But then this looks like it's in Fort Wayne, Indiana, which is kind of weird. You wouldn't think they would they're not particularly green. I've never been to Fort Wayne, Indiana, but they have an industrial compost. And then some of it's kind of odd, like Florida has one, maybe that's not that odd. Texas has two, like Dallas and Austin, I guess. And Colorado has like 20 of them. It's like they're big on industrial composting. California has quite a few, but then Oregon has none. So it's kind of an odd thing. Like there isn't a lot of industrial composting around the US. So the PLA is really not going to compost. Like people saying it's a biopolymer, that's a lie in Cincinnati. Maybe if you're in Colorado, it's a biopolymer, but basically anything you use here, it's not going to compost. Anyway, so those are the two. This is what one type of industrial composter looks like. It has to go to 22 megapascals, so 200 atmospheres pressure. It's got to be like 150 C. So basically, it's almost like a pyrolysis unit. It isn't like composting the way we think of it, Anyway, and you have to monitor the humidity. Like there's a lot of controls you have to put on it. And also, like, if you're going to go that route, like PET will already compost in that. Like all the polyesters will basically compost in that same machine. The byproducts might be kind of nasty, but basically, if you're going to claim PLA as a biopolymer, you probably want to start claiming a lot of things are biopolymers. So it's a little bit odd. It's biopolymer in the sense that you can biologically produce it because this is something in our bodies and you can polymerize that thing. But in terms of biodegradation, like PHB is looking like the best candidate as far as you can see, that for right now. Except, all right, so there's other routes. That's what this is about. So one route is like methane. So you get methane, like this is from India. Like here's a video of this, we don't need to watch it. Basically, you put your compost into a bin and it's anaerobic degradation. So if it's aerobic degradation, it makes CO2 and compost, like the dirt stuff, right? If it's anaerobic, it makes methane. Like the byproduct is going to be methane. So in India, like they just have this in the backyard, they tap it, and the tube goes right into the kitchen and they cook with it. So they don't buy gas, they use that. And in China, the government has like funded this so that kind of methane production, especially in the rural China, produces like a huge amount of their energy. It's like, so China's big on this thing, and India looks like they're trying to implement it to reduce their consumption of fuels. Here's some other bioreactors you can build in your backyard if you want. These are totes or something. They're like liquid from a chemical plant. If you're gonna, so these are just chemical plant totes, and then you reuse those things to turn them into compost, methane producing things. So there's a bunch of these. Like you can look on the internet to figure out how to do this. This is a 50-gallon drum with a weighted lid to get the pressurize the methane. This is just, you take some little tents. So these are like glove boxes and you put manure in it and that'll make methane. You can take the methane off and do it anywhere. They're doing it in Kenya or something, biogas in Kenya. So you can also do that on an industrial scale. So you can go to a pig farm or a chicken farm and you can set up a digester that's an anaerobic digester is going to make methane. Municipal sludge, so that all the sewage plants are kind of producing methane. Some are trapping it, and any kind of waste can go into this thing. You can put oil into it, it'll make methane, right? So you can kind of put anything in this. And then you can use that as a heating source, cooking fuel. And then our interest is that you can make plastic chairs out of it. So methane is one of the feed ingredients they can put into a chemical process with several steps that will lead to like polyethylene or any kind of plastic that you want. This is how we stand in the world in terms of the methane kind of use. Methane is also industrial byproduct, and it's also natural gas, and when you have oil wells like fracked oil, most of the stuff you produce is methane from fracking, right? So methane is also a feedstock. So he can do mass balance accounting and have the methane feed coming from fracked oil in Pennsylvania and Ohio and New York. And then you can feed that into the same plant that you're putting your sewage gas and whatever you got in the backyard. And if you get the cuts right, you could say it's 25% biopolyethylene that you get from that methane chemical plant, right? So this is kind of a mix. Europe's doing better than anyone else. So this is crop waste. So you can stick crop waste into this thing. That's one of these. They don't show it, but crop waste can go into these digesters. In Europe, that's a huge amount. And then animal manure is a good, like a super good source. That's like this guy in Kenya. So basically anybody can do that. And then municipal solid waste, I don't have a picture of that, but maybe you've seen it. And then municipal wastewater. So those all can feed into a digester to make methane. Europe's taking advantage of all that. Right, so they're pretty good. China's the next best, and this is animal manure, and again, it's like rural. So this is just rural places in China. The cities, they aren't doing this except for municipal solid waste. So China's doing good. Like it may be authoritarian country, but the trains run on time. You know, it's just kind of like we could be in that same position if somehow things shifted around a little bit. But anyway, and then the US, especially municipal solid waste. So basically the sewage plants make, or no, this is from dumps, right? This is Mount Rumpke tapping the methane. So all the Mount Rumpkes in the United States produce a sizable amount of methane. The municipal wastewater produces a small contribution compared to Europe. And the rest of the world, this is a mix. They can't really account for it. So this includes India and Africa and everywhere else where nobody's really keeping account of it. Right, so it's yellow, like you can't tell. Anyway, so that's the same thing of that table, but kind of in words. And then what happens to the methane? Well, a lot of it's used for like heating and cooking, then cogeneration, power generation, and the amount that's going to make a plastic chair is just like a tiny little bit of it to make bioplastic polyethylene. It's just a little teeny bit of the total in 2018. It's probably close to that now. Cows make methane too. That's kind of so methane's a greenhouse gas, and it's got, I think, 5 times the greenhouse gas effect as carbon dioxide, but it degrades in the atmosphere in like 2 or 3 years. Carbon dioxide's forever. So basically the short-term impact of cows belching is worse than driving your car or something, you know. But in the long term, if you killed all the cows, then basically that would go away, you know. But your car thing isn't going to go away. So basically, anyway, cows could be a source, and there's actually people doing studies on collecting methane from cow stomachs. Like you can imagine you can get funded to do that because it's a sizable source because we eat a lot of beef. One of the big problems, so the manure makes methane. If you could collect it if you put it into a digester. And then the cows are also making methane and belching it. So anyway, cows are an issue, you know. People talk about cows. So anyway, so you can this is a digester company to make methane. There's a video here, might be worth looking at. There's a couple, anyway, this is what you do with methane. So you take methane and then you make syngas with it by putting it with water at high temperature with nickel catalyst. This was developed by Nazi Germany. Both the Fischer-Tropsch reaction and Fischer-Tropsch was developed before Nazi Germany, but it was only really implemented during Nazi Germany when they didn't have a supply of fuel. So they wanted to use this process to get fuel to run the war machine, right? So that's where this Fischer-Tropsch has a little bit of blood on it. All these processes are German processes, you know, so basically they all kind of tied into World War II. So, but now they're green chemistry. It's kind of odd how chemistry reactions, I guess, don't keep the scent of whatever they did before, you know, somehow. So anyway, you can take methane and you can do this reaction with water to make carbon monoxide, which is a fuel, and then hydrogen. So these are both fuels. So you can just burn this stuff. That's syngas, but you can use that to heat your house. or it could be city gas, like it's the same stuff. And then so that's a 700 to 1,000 C, and then you have the same, so you have CO and you also have water present. That's CO, if you put it to 400 to 900 at a lower temperature, this convert to CO2 and water. I mean, to CO2 and hydrogen fuel, right? So if you want to make hydrogen, you want to run both of these reactions together on one reactor and get just hydrogen out. Convert the CO to hydrogen. If you want to make polymers, you want a COH2 mixture to feed into the Fischer-Tropsch reaction. So it depends on your intent, what temperature you're going to run your reactor. Same reactor doing these two reactions, right? So you want to kind of cut it short and get just CO and H2, the syngas, which you can feed into this Fischer-Tropsch reaction, which will give you, it's like H2 plus CO will give you hydrocarbons if you put iron into it. And depending on the conditions that you run it, you can get different kinds of hydrocarbons out of this. So you can get basically long chain hydrocarbons from that, or you can get ethane or butane or propane. So this is a nice reaction if you want to make bioplastics, is you can make kind of any kind of monomer you want just by cooking syngas, which you can get directly from methane from a cow. It's kind of like cow makes this kind of fuel, the fuel makes the plastic, at least makes monomers, and the monomers make the plastics, like a 4-step operation. So there's always these plots that show this reaction. If you raise the temperature, you can get the hydrogen that you want, or you can get the syngas that you want, depending on what temperature you run the reaction. And then you have to run this with a different catalyst. So you need iron to do this Fischer-Tropsch reaction to get the alkanes that you want. Anyway, so that's kind of the operation that's the scheme for all these. There's a video of guys doing that. Not sure it's worth watching, but it's German, or it's Dutch, I think. So
what are you gonna ask the wizard for, Pixel?
Well, I'm not sure he's such a.
Oh,
So it's a Dutch guy. He looks like he's famous. He's doing Fischer-Tropsch.
So let's do first some paper chemistry. What is the Fischer-Tropsch reaction?
It's not a
The Fischer-Tropsch reaction is the reaction between hydrogen.
So we know hydrogen. We want to see the thing.
Process. Very interesting nowadays.
Wait. So he's got what is
It's called-
it show?
Can come
he
from
shows
different
the-
sources. For example, it can come from
Oh.
coal.
Yeah, so that's what the
Cool.
Germans wanted to do, was coal, like during World War II, to make gasoline from coal. That's hydrogen. At some point he burned something.
Clear fuels,
Oh, that's
You
the
can
fuel.
make
That's the syngas. That's
all
the
kinds
fuel.
of plastics.
Polyethylene, you can make ethylene they're burning. So the syngas, the fuel you get out of the Fischer-Tropsch is really clean, much cleaner than the petrochemical. That's the point. So yellow is carbon and white is just
Okay, well, here we have two
burning
burning
gas.
liquids.
It's
On the left side,
nothing in it.
we have Fischer-Tropsch liquid. On the left right
Just
side,
saying it's a much
this one,
cleaner fuel.
we have a
There is burning though, so it always is worthwhile.
A
And
reactor?
then she's showing how you,
We put
how they
catalyst
allowed to put the
inside?
catalyst syngas
Then we place.
out of it. And then she does some other stuff here. She shows a spectrograph of it. And then making olefins would be like ethylene and propylene.
From the Fischer-Tropsch reaction, we can.
So blah, 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 blah. She's nicer than him, but she just says like, you can do it. Yes.
The
Actually,
science
she's
magazine.
using the same promo,
From this?
same demo things that the guy had too. So I guess it says who it was anyway. So it's a big deal. Like people have been interested in this for a while. And there's this company. So this is a company. This is a bioreactor company. This AFR for methane production, which would feed into that shift gas reaction, the Fischer-Tropsch reaction. But so this
The
company is
Beaucage
doing this
AFR
industrial scale.
anaerobic flotation reactor is a
Not sure where this company's from, but they show the reactor.
AFR system composes of different units. The main units are the bioreactor, the biogas dissolving unit, the flotation tank, and the biomass recycling tank. In the bioreactor, the organics are biologically converted into biogas. In the biogas dissolving unit, the gas is dissolved in the effluent of the bioreactor. This takes place under pressure. In the flotation unit, the biomass is separated from the liquid. And finally, the separated biomass is flowing into a biomass.
Biomass is the stuff that's growing to make the methane. So you want to recycle that. You don't want to throw away your bugs. The bugs are kind of your catalyst.
Recycling tank.
So most of the operations trying to retain that, still get the methane out.
The incoming wastewater is pumped into the bioreactor through the influent distribution system that evenly distributes the liquid over the surface. The liquid flows upwards and is mixed well with the biomass in the system. The anaerobic biomass forms agglomerates, small flocks. The microorganisms in these flocks digest the organic compounds, such as fats, proteins, and carbohydrates. By various microbiological steps, biogas is produced. The microorganisms in the flocks produce biogas throughout the whole reactor. The biogas is collected in the headspace of the reactor. The mixing in the bottom and top parts of the liquid in the reactor is the highest. This is due to the recirculation of liquid from the upper part of the reactor back to the top of the reactor.
The chemical.
Another part of the liquid is recirculated back to the influent distribution system, where it dilutes the wastewater organic compounds. The energy-rich biogas is then collected in the headspace, leaves the bioreactor, and can be used, for example, in a CHP boiler, or can be upgraded into natural gas. The effluent of the bioreactor that contains biomass and purified wastewater is pumped into a high-pressure unit, together with a small flow of biogas. The biogas will dissolve completely in the effluent. The liquid with the dissolved biogas leaves the high-pressure unit and passes a valve that releases the pressure in the liquid. As a result, the biogas will form very small biogas bubbles. The liquid, biomass, and small gas bubbles flow towards the center of the flotation unit. The small biogas bubbles will attach to the biomass flocks and will lift the biomass to the upper layer. Here, the
Anyway, I thought that was kind of interesting, but actually it's.
highly efficient process.
Let me just click back. Yeah, yeah.
Track the methane, and we need a method to track the methane. And the biogas is actually a park gas or flue gas or the cow. So how can you track that?
And from a cow?
Yeah.
Oh, well, all right, there's people, no one's doing it from cows in actuality, but there's research groups that are doing it by putting a mask on the cow. They put a mask on the cow and they suck out the methane. So it's kind of like a CPAP machine, if you know what that is for a cow, except it's sucking off the methane. And it's giving it air so it can live, and then it's taking off the byproduct gas from it. And the methane is heavier than air, I think.
As I know, it's
No?
like heavier.
Okay.
So
All right.
if we
Butane
want
and
to track the
propane are
gas from the
heavier.
cow, we have to the OSD container, and this is not a humanities.
Yeah, anyway, there's people studying it. No one has actually put these kind of spacesuits on cows yet. You may see it soon in some field. It's a big problem for the atmosphere. Yeah, I think it's some high percentage, like 10% or something of greenhouse gas comes from cows belching. So it's a big it's worth kind of investing. If we had a government that cared, we would be investing in cow masks, or something, I guess. Maybe Europe will do it, or China or somebody.
Or we could just, not even want to be.
Yeah, that's another option. But I don't think, anyway, it's happening, slowly, that beefless world, but it tastes so good, it's like, anyway. So, yeah, so you can take that syngas, so you can do these German Nazi reactions and make the stuff you want. Or you can just feed, because it's possible to feed the syngas to bacteria and have them make this stuff, which are monomers for polymers. So there's companies, mixotrophy, I had to look up it. So there's allotrophy and heterotrophy. Allotrophy is like a plant cell, I guess, and heterotrophy is like us. Like we don't make our own energy, we eat it. And mixotrophy is something that is an allotroph or a heterotroph. It can do both. So there's bacteria that are mixotrophic, I guess, from what I understand, you know. Anyway, so it kind of has nothing to do with this, but it's right there yellow. So anyway, so yeah, so you can feed the gas in, put in your mixotrophic bacteria, and they'll make like all kinds of organic chemicals. This company, the Cincinnati Bio, does that. And Lazatech. So Lazatech, there's a video of their company too, how they do this.
The biggest
but-
lie we've been told is that neuropathy is irreversible and there's no cure. They do it on purpose. The medical system lies to
Anyway, so that's their process.
The
These are all
Lonzatec process converts carbon monoxide containing gases into valuable fuel and chemical products. These gases are typically produced by the steel manufacturing, oil refining, and chemical production industries. They can also be generated by gasification of forestry and agricultural residues, municipal waste, and coal.
That's one we're interested in.
The robust process is flexible to the hydrogen content in the input gas and tolerant of typical gas contaminants. The carbon monoxide containing gas enters the process at the bottom of the bioreactor and is dispersed into the liquid medium.
So they
Here it is
found-
consumed by Lonzatec's proprietary microbes as the reactor
Yeah.
contents move
they found
upward in the
bacteria
reactor
that can do
vessel.
this, and then they've genetically engineered some
Next,
too.
the net product is
So I think their
withdrawn
IP
and
is
sent to the
genetically
product
engineered
recovery
bacteria.
section. The product recovery section uses an advanced hybrid separation system to recover the valuable products
I think
and
that means
co-products from the
distillation.
fermentation broth.
I mean,
The water is recovered
know why
and
they
returned to
say
the
that.
reactor system, minimizing
Anyways,
water
that's
discharge
it, I
from the
guess. Anyway,
product.
it's kind of, they do have a video about what they do. So that, and there's that company and this other company, the other company, it's very hard to find what they're doing exactly, but anyway, so that's one thing you can do with the syngas. So that's like methane. So this methane's one section, and then pyrolysis oil, we've already kind of talked about a little bit, but it's a little bit more in depth, I guess. You can, if you take wood and you just heat it up at 100 degrees, it'll just stay at 100 and you keep heating it until all the water's gone. Then you have dry wood. And then you heat it up some more, and then at 270, it starts to decompose, and it's exothermic reactions are going on, and then you get charcoal from that. If you heat it up, so surprisingly, if you heat it just to that range, you get charcoal, and all the good stuff goes off in the gas, basically off gas, right? But if you want to get bio oil, you have to crank up the temperature, and then you can to 700 C, and then you get bio oil, and then syngas is even higher temperature, I think, the way this works. So it's kind of, anyway, what's his name? Mao Bing Tu, right? Chemical engineering department. This is what he does, just this stuff, like cooking bio things to make oil and goo and things, you know, so that's his expertise. But so anyway, I thought there was a better description of that somewhere here, but maybe not. The whole process of that. But anyway, so you can get that, and that can be substituted in as like an oil, just like as if you had crude oil, this pyrolysis oil from that. I mean, and then there's another process that's without water. You can also take, so this is kind of dried biomass, but sometimes agricultural stuff is wet. So if you have wet biomass, you can do this hydrothermal liquefaction under pressure. So 210 atmospheres, 350 C. You can cook wet, gooey, whatever, mowed your lawn stuff, and just make bio oil with twice the energy density of the pyrolysis oil. But it's more expensive because you had to pressurize it. So there's two processes, just a normal pyrolysis and this hydrothermal liquefaction process. And then there's other things like we already talked about, black liquor and rubber oil stuff. But anyway, so once you have that, then they call that pyrolysis oil, then low temperature then pyrolysis oil, then that can be used to make bio BTX, so benzene, toluene, xylene. So normally from a petrochemical factory, you crack the oil and you make BTX. Then you feed it into a distillation system to cut to get the things that are going to make styrene, polycarbonate, nylon, polyurethane, polyester. So the different cuts from it, from the BTX, in other words, benzene, toluene, xylene, the different forms of xylene, feed into different polymers. So you can make any synthetic polymer by cooking your whatever organic stuff. So that becomes bio polystyrene, bio polycarbonate, bio nylon, bio polyurethane, bio everything. Right? So you just feed it in. And if you put a cut of that, you can say it's 50% bio polystyrene. So there's an industry to do that. I mean, you're kind of selling it for, so this is showing like the bio BTX, just after the catalytic reformer, you can mix bio BTX with petrochemical BTX. So you can mix it right at that stage, or you can mix the products. You could do anything you want, basically, and then you can, whatever comes out and you use it, you can say it's whatever fraction bio. Right, so it's a nice deal. Then you can also, this should have come before with the methane, right? It's another use for methane. You can take methane and directly put it in with bacteria and make PHB from it. So bacteria, this New Light companies, there's two companies, New Light and Mango, and they're both in California. And this is pretty typical of the startup companies. Like there'll be one in LA and one in San Francisco for some reason, like Beyond Meat and Impossible Burger. One's in San Francisco, one's in LA. And all the startup companies have like one in LA, one in San Francisco, none in Ohio. You know? So anyway, anyway, PHB from methane is like something people are doing. And then anyway, this New Light, they bring up like that there's, I guess their bacteria originally came from reefs or something, and then somehow they figured out that the kelp or things that are growing have PHB in them, and then they realized that it was somehow getting it from methane and whatever. I'm sure it was like an NSF project someone did, and they realized you could make money off it. So they're making pretty nice looking PHB from this whatever source bacteria using just methane as a feedstock. So is this biopolymer of the methane? Most of the methane comes from petrochemical, from cracking, or from fracking, right? So if you take fracked methane from Pennsylvania, you ship it to Huntington Beach, California, is this a biopolymer then? You know, I don't know. I mean, things get pretty complicated when you have this kind of chemical operation going on. That would be a good question. Like, is that a biopolymer at that point, or is that a petrochemical polymer? You know, because most of the methane we're throwing away, or cows are belching, and you know, whatever. And this Mango company has a flashier. I mean, the New Light seems to be industrial. Like the things they show are things you could feed into an extruder, and then the Mango was a little bit more fluffy looking stuff, like fabrics and whatever. So anyway, so that's another option. And all these things have startup companies involved. I mean, some of it, like when it goes to Degussa, whatever they are now, and then like all the petrochemical companies, those are actually big, large scale productions. And these are mostly like smaller scale operations that are trying to get bought up by Degussa so that they can cash in and move to New Zealand or something. But anyway, and then the mango companies tying in though with, and they have one operation where they've gone to a municipal waste source for methane to produce PHB. So PHA means they're also doing valerate copolymers with it. But so anyway, so they're trying to expand, you know, and they have a couple operations that are more than pilot plant, but less than anyway, so that's one part of this. Then the wood stuff, right? So lignin is a big waste product. It's a polyaromatic. Can break down into these kind of monomer-like materials. And there's companies that are doing this kind of lignin thing. I didn't find the one. There's one there is one in Finland, the VTT. VTT is like a research institute in Finland. They do a lot of different things. It's kind of like the MIT of Finland, but it's a company, it's a government-sponsored company. They don't, I don't think they give PhDs, maybe they do. Anyway, VTT is another one doing this lignin processing because there's a lot of wood in Finland. So, and then LignoBoost and LignoForce are two companies that do this stuff too. Lignin's a big waste product, we mentioned it before, and then people are trying to make polymers with it. So they have like black liquor turns into something that's useful. Mostly it ends up to be a brown powder that they end up with. It doesn't look that great, but it can be converted into chemicals. These are the other, like, I'm not sure if we looked at this already, but glucose, and if you take glucose and put it into a polymer by hydrolyzing the hydroxyl, you end up with kind of an ether bond. And then that can be either, so it's stereochemical. So these are stereochemical rigid, and then this thing has either can go up or down kind of. So if it goes up, it's a beta. If it goes down, it's an alpha. It isn't exactly up and down. It's how the handedness of the bonds go here. But the way they've drawn it here, it's up and down. So basically beta and alpha, and it's 1, 2, 3, 4. So it's 1, 4 beta. And this is 1, 2, 3, 4, 1, 4 alpha. And if you have branching, it's 1, 2. It's 1, 1, 2 would be a branch. So you go like 1, 2 or 1, 6, 1, 2, 3, 4, 5, 6. So if you have a reaction, a bond that's going 1, 6, that's a branch. 1, 4 is the chain. So starch has these two chemicals in it, and this alpha bond you can eat. So like your body can break down that bond. We have enzymes to break that down. This bond, you need a bacteria to break that down. So basically that the difference between the two, and the reason why like rabbits and cows can eat this and we can't, they have bacteria in the stomachs that kill that thing, we don't. Right. So if you can put this into a fermenter, you could potentially get glucose out of it. We can put into another fermenter and make whatever you want from. Right. But so the problem is that this stuff's crystalline, right? So it isn't just breaking that bond. You have to kind of chew it up somehow and get rid of the crystals. And you can't, if you heat it up enough to melt the crystals, it burns. So basically, it's hard to kind of get rid of cellulose. You know, the other starch is easy, cellulose is hard. But there are bacteria that, and so the timing, you know, the time that you do it, and if you cook it different ways. And the other things in wood, so basically cellulose, lignin, and this hemicellulose, which also has the beta bonds, and then it has branching. So it's at 1, 2, and the 1, 4 bonds in it. So it's a highly branched structure, and cellulose is kind of linear. Cellulose is a linear molecule. So that the difference between hemicellulose and cellulose, and lignin's the third component of wood. And starch is another animal that's come from potatoes and corn and any kind of starchy thing that you can think of. So anyway, so once you can break these down and make sugar, then you can make all these monomers from it, from biochemically, or you can make all these monomers. Basically, you can get these from fermentation, everything here, and those can all be used to make biopolymers from wood. So generation 1, generation 2. Generation 1 is using corn and sugarcane to make ethanol. And generation 2 is using this stuff to make ethanol. It's like the generation 1's been going on for a long time, and like the Midwest, like Iowa, has tons of these plants, right, doing this. The generation 2 is like a newer thing, but there still are some plants using wood to make make chemicals to make plastics. I think I'll show a couple in a minute, you know, but then the other source of like biopolymers is oil. So you can, so oils, so you can have vegetable oil like palm oil, or you can have animal oil like lard. So like, in fact, in Cincinnati, there's Emery Oleochemicals on Vine Street, and they're doing lard. So the largest consumer of lard in the world. So the price of lard is determined in Cincinnati. Most of it comes from Texas, and it's shipped here by train. These tank cars come into Cincinnati, they're full of lard. You have to heat it up for it to flow. Anyway, it's not a good place for like a Hindu or something to visit, you know? It's literally liquid cows going through pipes. Then right next door is a BASF plant that uses palm oil to do the same thing. So the two like right next to each other. I think they might even share like a power generation plant or something. I think it all was linked to P&G at some point, and then it was spun off. These were like spin-off companies. BASF isn't, but it was bought and sold. Anyway, so this you saponify it by splitting off glycerol. So it's a 3-hydroxyl, so that can be used like ethylene glycol will be 2-hydroxyl, so you can kind of use that in polymerization. It's also like fake tears and whatever, right? Glycerin, glycerol. So that thing that breaks off, and then you have the fatty acid, which is some long chain alkane or alkene. I don't know if it's saturated or unsaturated. Then it's got this hydroxyl on the end. If you want to make a detergent, you sulfonate that. So you get sodium sulfate, that end group, or you can have other kinds of end groups. So you can tune this with ethers to make it soft, better detergent or something. Like so there's different designs of that. This end group. The simplest one is to put sulfuric acid in and make a sulfonated fatty acid as a detergent. So the difference is like if you just have the fatty acid, it crystallizes. So you get a bar of soap. And if you want to have liquid detergent, you got to put a sulfate group at the end so that it doesn't crystallize. I think that's the difference as far as I know. But so anyway, so it's a bigger market for sulfonated. So there's industries just geared around all this process because it's so much and it's value added products and it's real simple chemistry to do this. Anyway, so these can also be fed in to make plastics. This, like the unsaturated ones could be polymerized, I guess, if you wanted to make some weird polymer, or you can break this stuff, the fatty acids down into chemical units and make whatever you want. So it's like they're ranked by the C whatever. So it's like dodecanol is C12 0, and then all these others like palmatic acid is 16 0. So 0 means there's no unsaturated bonds in it. And then oleic acid's 18 1. So it's like 18 carbons and 1 unsaturated group. That's one way to name these things. Anyway, so that's kind of the sources that you can get for biopolymers. I mean, that's kind of what you have for biological sources of things. Then there's a lot to this business, actually. You know, so people rank so it's a pretty big industry, this whole bioplastic thing. But so and there's a lot of people studying it. So they've named everything like primary feedstock and secondary feedstock. So primary is like you kind of grew it used to make bioplastics with. Secondary is a waste product like black liquor from lignin thing. And tertiary is like paper waste, like recycled paper or whatever municipal wastewater. So there's 3 kind of sources that can feed into that, all those different things. It's kind of a mess of different stuff going on here. So, and then this dedicated feedstocks is a problem, like you're competing with food and that sometimes, or with wood that you're going to use to build things or oil or whatever. So these are all mostly edible things that maybe you wouldn't want to use if you don't want to have people starving. Then these are like waste products, all kinds of waste products that you could use to make this stuff. So it kind of fits in with that scheme too. So it's just different naming schemes. So I think we know most of those things. This just shows like, I don't know, it's a diagram from NREL's, the National Renewable Energy Lab in Colorado, which might be shut down in a couple of weeks, you know, who knows? Anyway, DOE, so it probably will survive. Actually, they've survived for a long time under the radar, but it's not a big lab. So Stover is like whatever you see in the field, and you can roll it up and you can feed it in, and you can grind it. And you can feed it into like steam and acid, pre-treat it, and then separations. flocculation, put lime in to digest it, then put it into a reactor with bacteria that are going to break up the cellulose into sugar, to glucose and fructose, and then feed that into or and at the same time you can ferment it, then feed it into separations. So this is kind of classic chemical process. Then here they're burning some of it. Anyway, so that's kind of a bio plant using this as a feedstock to it. Agricultural waste, which is it's kind of a big contributor. And this is just showing like a biodiesel plant, like similar things. So whatever waste product you have, here it's like cooking oil going in, and I'm not sure, I don't know what CNR technology is. I tried to figure that out, and actually I couldn't figure it out. So anyway, it's just showing a schematic of how biodiesel production would go. So that would end up giving you bio oil that you could use to separate into, or you could use it as a fuel, or you could separate it into monomers that you use for polymers. So this is the generation 2, one of the generation 2 plants. I think it's in Iowa, or I guess this is the company is in Michigan, but I think this plant's in Iowa. So it's like taking wood chip waste and then making ethanol out of it that could be used to make plastics. So I already went through that chart. There's added features. This is just breaking that down into like the list of all the possible polymers in each of the 4 categories that exist. So maybe it's of some use to have everything listed. Let's see. So basically, this is direct production of ethylene to make polyethylene from natural gas. It's just a schematic to show that. So this oxidative coupling of methane is a new technology. So basically, you could take natural gas, or you could take methane from this Mount Rumpke, and then suddenly make it into ethylene monomer, right? So this process didn't exist until like 10 years ago, and a company came up with a nanowire catalyst. This guy's Silura. So this is kind of a big deal. Like you can directly take either frack natural gas, or so this is like a boon to Ohio. Like, I mean, because we have a lot of frack natural gas, ethylene's a value-added product here. So basically, this magic catalyst that they made, I'm not sure if it describes it here, but it's basically a nanowire catalyst. That's how they describe it. And it's some metal, I don't remember what it is, like nickel or something. So this is this Silura, like the IP thing that's going to probably made them a fortune already. We can just pump out ethylene, putting in natural gas, or Rumpke, whatever Rumpke gas is, just directly make ethylene from that. So depending on where you got the methane, that can be a bio, or if you have a mix, then you get a cut of whatever down here is bio or not bio, polyethylene. You can make polypropylene with it too. So that's where the natural gas is. Someplace I got this map, but that's kind of where the frack gas is kind of in the United States. So we got like upstate New York, Pennsylvania, and then like along the Ohio River. Right, and the traces down all the way to Tennessee, but basically most of the operations like right in here in upstate New York for getting frack gas. And that means that the nice thing about this is it can be done at site. So this is saying, so the supply map is removed from the demand, meaning that if you're gonna get the gas here, then you have to ship it to Chicago in order to do some process to turn it into whatever you want to turn it into. But if you can convert it, I guess they're arguing that if you can convert it at site, and these things can be made like small scale, I think you can make them just for the size of one oil well. And it'll just be pumping out ethylene instead of methane. And then that can be immediately go to a processing plant. Like, so basically ethylene, I don't have the map. Basically, there's a map that shows the ethylene pipelines that crisscross the United States. So you can feed right into the pipeline. right? They go all over the United States. So basically, you can feed right into a pipeline and just pipe the ethylene. Right, so anyway, that's happening. So yeah, that's generation 1, generation 2, like ethylene. Okay, there's a lot to it here. So yeah, we can kind of end there. I think we don't need to go on too much here. I'll try to squeeze some of this in later on, but there's a lot of companies doing different things to make the biopolymers. That's the point, I guess, that there's like so many different angles on it. It gets to be a little confusing because you kind of, I mean, you can make so many different products. The things look the same as what you have. You can label it bio or not bio. You can say it's a fraction bio. And then you can also make actual PHB. You can make it directly from methane. I mean, there's so many options, right? It's hard to tell. Like, you kind of need an economic analysis of the whole thing to figure out where it's going to fall together, I guess. But the bio, yeah.
PHP has its own problems, so right where it's like hard to scale it up because it's
Yeah,
because you can't just add pressure to it just to speed it up.
yeah.
So
Also, the TG isn't great too. Yeah. None of them are going to exactly be matching what we have now. Yeah, so people are going to have to decide what they want to do, I guess, about it. Yeah, it's true. PHP isn't the perfect answer, but there's been so much like there's so much IP even coming out now on it that it seems like they're tuning the properties. They have a pretty good handle on how to tune the properties. Whether that becomes economical or not, I don't know. It's pretty hard to tell. Like, I mean, it seems like if it was going to be economical, you would be seeing a lot more of it right now, I guess. There's some of it, but mostly it's by choice. And some people want to use bioplastics. Some people don't. Some people hate bioplastics. I think it's like a secret thing that's happening. Someone's doing something to change the world. Someone was saying that the cars shut off at the red light now and then they start up. And then the guy was claiming that it was like because the starter companies had taken over the world. The car starter companies, could be, I don't know. Anyway, who knows? But yeah, so the bioplastic seems like a pretty viable thing to me, though. Like, it seems like you could replace already existing technology, you could replace everything we're using with some kind of bioplastic if you wanted to do it. So it's a question of, do you want to do that or not? I think Europe's decided they want to do it. China's decided they want to do it. And the US has decided basically they don't want to do it, I think. So, maybe we'll just live with big piles of garbage plastic and the rest of the world will have kind of clean beaches and things. As long as we don't export it, but anyway. All right, so yeah, so I've successfully consumed an hour here. So yeah, so Tuesday should be interesting. So try to come with some questions. Like if everyone has a question for, it would be good. Your boyfriend should come with questions. In fact, he can dominate the whole thing if he wants to, Yeah. Yeah.
So I'm gonna sit in the front, so I probably won't sit with him. I'll be on his own, like
All right.
against class.
Tell if he wants to talk to her, sit up front and just ask questions. Like people always move to, I'm teaching a class that thermal class has got 6 people in it. Like, and it's in a small classroom, but 4 of the people sit in the back row. It's like, why do they do that? It's like, what is going on? Then one brave person sits in the 3rd row, and like everyone else is in like the 4th row. Well, these 2 other people are in the 4th row. So it's like,
All my friends sat in this row and they don't come.
yeah. Yeah, that's pretty crazy. I don't know, when I was in grad school, I always sat in the front row, which turned out to be dangerous. Like there was one guy who taught at 8 in the morning and he taught continuum mechanics, which is the most boring subject on earth. And I'm not like a morning person. So I'd be sitting there like my eyes, like gluing my eyes open, and I eventually would just nod off, So, so it can be bad, but I still stuck it out. I mean, I'm surprised he didn't come over and whack me, it's like when you're drooling, that's when they know like something's going on. But anyway, the subject though, that was pretty boring, but it's important, but it's a boring subject. Anyway, so yeah, it surprises me when people don't sit in the front row. All right, here though, you get a neck ache in these rooms if you sit in the front row. That's one problem with it, so. I was sitting kind of the second row or whatever, but. Anyway, all right, so, yeah, Tuesday. So we'll have the P&G person, should be good. Let me kill this.